Okay, so today we are going to start another chapter of module 2 itself. So this is going to be our chapter number 7 from module 2. Very important chapter. It is called the model estimation. So what happens when we build models? There are a lot of parameters that are there into these models, whether it is a simple logistic regression or it is a more complex neural network. There are a lot of parameters that are there in the model. A model is actually made by the parameters that it contains. So how do we estimate those parameters? So that's the chapter all about. This is chapter 7, and we'll be left with 3 more chapters after this chapter in module 2. One is on evaluating the quality of models. That is chapter number 8. It's a very small chapter. And then chapter 9 is about natural language processing. And chapter 10 is on generative AI. And then we'll move on to module 3. So let's start chapter 7 on model estimation. So, let's start with very basics. So generally there are 3 fundamental techniques to do model estimation. One is called the least square approach. What happens in least square approach is that we minimize the residual of the sum of squares. So what I mean is that, let's suppose you have created a model or you have estimated model, and your let's suppose your equation seems to be like y equals to a function of x1, x2, x3, etc. Now you get some values of y, and then there are some actual values that it should contain. You find out the difference of the two and you square them, because you don't want to have negative values and positive values overcompensating or clashing with each other. And then you find the try to minimize this value. So it's called the least square approach, and we'll get into more details of what least square is, but this is about minimizing the residuals. Okay, the second approach is called as maximum likelihood. What happens in maximum likelihood is that it is the reverse of least square. So we try to maximize the chances of our estimate to be as close to the real values or the labeled values. So that's the maximum likelihood. And there is third technique which is called as the method of moments. So in method of movements, there are movement restrictions, based on the context, based on the distribution of values, etc. We can find some constraints, or we can find some restrictions based on which we can apply those constraints and say that these values should always lie between so and so, etc. We are going to talk most of this chapter about least squares and a little bit about maximum likelihood. We will probably not talk so much about method of movements, because we don't use it so often in machine learning. Okay, so let's start with what is actually a loss function. Okay, so it all starts with this loss function. You can also call this as an objective function, and this is very important. This loss function is very important, because everything that we shall optimize is going to be the optimization of the loss function itself. Okay, so generally there are 2 methods of model estimation. One is, so of course there are these 3 methods, but I would say there are 2 techniques to do model optimization or model estimation. One is called analytical methods. Okay, so what I mean by analytical method is that there has to be a mathematical way to find out these parameters. It's not just hit and trial. There needs to be a mathematical way. And or maybe let me try to put it in a more detailed manner, that when I say it needs to be optimized, in a lot of cases, if you have already read in your school or elementary maths, the differentiation and integration, the rate of change of these values will minimize, or they'll tend to zero when it gets into a very very optimized place. So when we talk about analytical methods, we'll talk about differentiating these loss functions with respect to a parameter, equating them with zero, and mathematically trying to find the most optimized values of those parameters. Okay, the second way of finding parameters is a kind of a numerical methods, which is not analytical, hence it is numerical, which is more of like hit and trial. But it is not just making random guesses. There is a method to madness in numerical methods also. What parameters should be changed, what should be the direction of the parameters, etc., etc. So these are these are and it's not that analytical methods are always better than numerical methods. So if your dimensions are very very large, it is very hard to find out the optimized values using analytical methods. So in those circumstances, numerical methods may become easier, or may become more handy. Okay, so let's move on to one of our analytical methods, which is ordinary least squares. And there is a lot of exercise and contents in your GARP material around ordinary least squares. This forms one of the backbones. So what happens in say ordinary least square, as I was telling you earlier, that if my y, or maybe I call it y, but somebody can call it something else. This is if it's let's suppose we are talking about a logistic regression or a linear regression. In case of a linear regression or a logistic regression, your y can be beta naught plus say beta 1 x, and maybe there is some error term mu. Okay, now we are trying to find out the residual sum of squares. So some of these abbreviations are very very basic, so I'm not going to write what RSS means. It means residual sum of squares. So it means your calculated value minus your actual value, and you find the sum of squares for that. Okay, and then you do this for all of your values from 1 to n. And if you want to make the mean, because this is going to be for n values, so very very simple, we divide this by n, but same, and then it is called mean sum of squares. No, not too difficult to understand. Okay, so that's on the ordinary what happened? Okay, nothing. Residual sum of squares, etc., that I was telling you. So if I have to expand this term, okay, let's try to expand this term RSS. So what is my y? Y is my beta naught plus beta 1 x plus mu. So my RSS eventually becomes yi, which is my actual values, minus beta naught minus beta 1 x square, and then I sum this for 1 to n. Okay, now as I was telling you, in analytical methods we tend to differentiate this with the parameters that we want to estimate. In this case it is beta naught and beta 1. So we will try to differentiate this with beta naught first, so RSS, and then we will try to differentiate this with beta 1, equate them to 0, and then find the values of beta naught and beta 1. You don't have to get into the derivations of how this is derived, but I think it is good for you to remember the formula that beta naught is going to be your, so when I say y bar, it is the mean value of y into x bar. Okay. And how do you find the value of beta 1? Beta 1 is going to be your sum of x and y. So if you have n values of x and y, you multiply them, you add them all, and then you take the mean values of x and y, you multiply them with n, and you divide them with xi square, and then n of x bar square. Okay, I think that's the right formula I have written. So n is your number of values, x bar is your average of x, y bar is your average of y, xi, yi are individual values. So that's how it is. So it's always good to remember this. Most likely you will get probably a question on this where they will give you a set of values. Let's suppose they will give you this kind of a tabular data. This is your xi, this is your yi, and this is probably your y bar, or maybe not y bar. This is your xi and yi, and then they'll try to ask you what is the value of beta naught and beta 1. It should not be very hard. So you multiply xi yi for all of them. That's what you do here, xi square. And then if they, let's suppose they'll give you 10 values, the value of n is 10, you find beta 1. Once you find beta 1, you replace beta 1 here, and then you find the mean values of x and y, and then you do this subtraction and find the values of beta naught. So that's the ordinary least square, and this is how the values are derived and found, and this is how these parameters are estimated. But we took a very simple example of a linear regression that also in one variable. So what happens if we have to if it is not one variable, if it is multiple variables? Okay, so when I say multiple variables, your y becomes beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, and so on and so forth. Okay, so since the complexity becomes very high, it becomes difficult to differentiate or find these kinds of analytical methods to solve this. So in this case, it is always advised to use numerical approach. Okay, if you remember, we spoke about analytical and numerical approaches in the morning, in the early beginning. So we should use numerical approaches. Okay, so next reading is about something called as hill climbing. A lot of these names are also very intuitive. You know, this came from the intuition of, let's suppose we are in x and y, and your loss function supposed to be, or whether it is a loss function, whether it is a maximum likelihood, or you know, anything else. So if it is a loss function, you need to go down the hill. If it is a maximum likelihood, you need to find the top of the hill. So you find a value. Let's suppose you are here, and let's suppose you are trying to do a maximum likelihood. So you want to maximize your function. So you find a value here, you find a value here, you see which one is better. So you find this is here. That decides the direction of your search. You keep going up till the point you reach here, where you know that even if you go here or here, it is not going to improve your value, and then you find out this is my most optimized value. Now, as you can really see here, there is a better optimized value here, and this is the problem with this kind of an approach. So this place is called as local maxima, because if you start from this point, this is your local maxima. Okay, and this is probably your global maxima. So in hill climbing, And if we use the very basic strategy of hill climbing, there is a chance that you will get stuck in local maxima. Okay, so it is more of a heuristic method of finding the parameter values, but this is what hill climbing means. I don't think you need to get into the more details of this, but you should understand what hill climbing means. Okay, we already spoke about maximum likelihood, because I was talking to you about finding these maximas, which is again maximum likelihood, instead of the least squares and finding the optimal values of least squares. So again, let me give you a little more details whatsoever is given in your garb material. So y is equals to, so I'm talking about a linear or logistic regression. 1 upon 1 to the power of 1 plus e to the power of minus of the entire function, beta naught plus beta 1 x1 plus beta 2 x2 and so on and so forth. Okay, so this is and plus maybe let's also say that there is an error term. So this is your function. This is a function that gives you the probability of 1. Okay, so your probability of 1 is this thing, and your probability of 0 is nothing but 1 minus probability of 1. Okay, now and this is, let's suppose this is yi, for yi, and I'm talking about xi is here, so this is for a particular instance of y. The probability of 1 and 0 can be found like this. But if we have to find the probability distribution function, okay, the probability distribution function for all the values of y, then how do we generally do it? We find the probabilities of 1 and we multiply this by 1 minus probability of 1, raising this to the power of 1 minus yi here and yi here. That's generally how your distribution function operates. So if I try to expand this, if I say that what is going to be my loss function or my probability distribution function for the entire values of y, it is going to be my loss function for y1 multiplied by loss functions of y2 multiplied by loss function of y3, and so on and so forth. Okay, now each of these individual values y1, y2, y3, as we have seen, and let's suppose we call this as a function f of I, which is equal to y, etc. So this is nothing but this is going to be, this might look complex. I'm just trying to formulate these equations so that you know the intuition. It is very less likely that something like this is going to come in the paper. The papers are extremely easy, but it is good that you understand how these probability distribution functions etc. work. Okay, so f of loss function of y1 is going to be f of y1 raised to the power of y1 into 1 minus f of y1 raised to power of 1 minus y1. Okay, and this is for y1 and y2 and y3, so this will carry on and on and on. So this is going to be get multiplied for y2 and y3 and so on and so on. So you may have used this sigma function a lot of times when we say that this is how if there are multiple variables that are added one after the other, you use a sigma function, right? When you use a sigma xi, it means that it is x1 plus x2 plus x3 and so on. Similarly, there is a function called as pi, and when I say pi of xi, it means that x1 multiplied by x2 multiplied by x3. So it is a kind of a notation to be used for simplifying or rewriting some of these equations too, so that it becomes mathematically simpler. So I can write this equation by saying pi of 1 to n, and then this is f of yi raised to power of yi 1 minus f of yi raised to power of 1 minus yi. Okay, now this is pi function, so it encapsulates everything that I have. Now if I have to differentiate this, okay, if I have to differentiate this, it is very hard to differentiate when there are multiplication terms. So in such cases, what we generally do is we take log of both sides. Again, skip this if you find this complex, but I can't stop myself from taking this to a logical end and telling you how we can analytically derive some of these values where maximum likelihood is to be used. So when your multiplication terms will become your addition terms when you take the logs. Okay, so now what happens, instead of pi you can write sigma, because now multiplication becomes this, and if you look at this particular term, this is going to become your yi into your log of f of yi. Okay, and again this is multiplication, so this is going to become 1 minus yi log of 1 minus f of yi. Okay, and then it is for 1 to n. Now your values of y can either be 1 or 0, because we are talking about, say, a logistic regression. So if your value of y is, let's suppose, 1, so then this becomes this term is going to become log of f of yi. Let's suppose y is 1. So when y is 1, this becomes 0 and this becomes 0, so you don't need this term. And if your value of yi, so this entire thing becomes this thing when your y is 1, but y can take values of 1 or 0. So when y is 0, this becomes nil and this term will remain. So I will say sigma 1 to n. So when y is 0, this anyway becomes 0. When y is 0, this becomes your yi log of 1 minus f of yi. So this is y equals to 0. Okay, so and anyway this is 0, so this will also not remain there. So this is how you will get this log of y function, loss function y, and whether you want to minimize or maximize L, or you minimize or maximize the log of that function, it is similar. So you can differentiate this now with respect to the parameters that you want to estimate, and then it is going to give you the values of those estimates. So this is how the maximum likelihood function will operate when it comes to model estimation. There can be more videos on the internet of how this actually happens, or there can be some exercises where you can do some exercises, but this should be good enough for you to understand how this equation works, and good enough for you to answer the questions that would be there formulated in the exam. They don't want to test you mathematically, or they don't want to give you these equations for differentiation or getting the logarithms, but they'll only test you for your core understanding. Okay, so next reading, so I think enough of math now. Let's move on to something simpler. So there is a concept of overfitting and underfitting, and this is all model estimation. Okay, now what happens, okay, let me take an example. So let's assume this is your x, and there are two variables, x and y and things like that. These are your points. Okay, so these are your points, and now you want to find an equation that goes through it. Now in case of, let's talk about underfitting. Okay, let me see if I can pick some color. Okay, so this is underfitting. So in case of underfitting, I'll try to oversimplify the equation that passes through these lines, whether by minimizing the loss function, we spoke about ordinary sum of squares, etc. So I'll make a line like this. Okay, so this is my underfitting. I'm trying to oversimplify the estimates of my data. Okay, I'm just trying to say this is kind of a linear thing. Now in case of overfitting, okay, in case of overfitting, the problem is that I try to I try to also fit the noise that comes with data. So whatever data we collect, however we collect, whether it is a survey data, whether it is any form of scientific data, there can always be some noise, instrument noise or any other noise. Now in case of overfitting, I try to fit it like this. So I try to fit everything that is there in data, and let's suppose there is a, let me go back. There is another data point where, in case of testing, I had hidden some of these data points, and let's suppose there was a data point probably somewhere here. Okay, if this is our data point X, now this red line and green line, both of it is not going to estimate it properly. In this case, it seems that red line is going to estimate it properly, but this X can be, let's suppose, here as well, X dash. So because this red line is trying to oversimplify the model, the green line is trying to overestimate the model. So, and this is in your machine language terms, these are called as overfitting and underfitting. So what is it that actually we should do? We need to optimize, and we need to find, in this particular case, it seems to be a kind of a parabolic curve. So if we are able to find this parabolic curve, it is going to be the actual estimate for the underlying model. Okay, so that's a more balanced approach, but this is what underfitting and overfitting means in case of machine learning, and especially in case of estimation of models. Now the next reading is going to be a little more complex, a little more math is going to come. It's called as gradient descent. Similar to the hill climbing that we spoke about, but in case of okay, so let's talk about this gradient descent. So again, I'll go back to the diagram that I always do, and then this is kind of a curve, and let's suppose let's find out the minimum value right now. So this is the value that we are trying to find out, and let's call that minimum value as your Wi star. Okay, and this is your Wi, and this is, let's suppose this is your loss, and this is your W. Okay, now this is the value that you want to find out, and let's suppose you make a random guess and you start from here. So that, let's call that as W naught. So so you find out the you find out the tangent of your equation, or your and then when you find the tangent of that equation, which is nothing but the derivative of that equation, you find out what is the slope of that equation, and based on how much you want to change your value, you can, if you are doing it very, very slowly, you will finally come here, maybe you'll pass this, and then you'll come here, and then come here, or eventually come here. Okay, so that's how your gradient descent works. So again, what we are trying to do here is, okay, so let me open a new presentation, and I'll also try to put these presentations at either some GitHub or somewhere where you can download it. Okay. Okay, so we were talking about this loss function, that diagram that I was telling you, and we have to find the differential of that loss function with respect to my wi. Okay, so this is the and then I equate this to 0 so that I find out the value of optimized value of wi, which is the wi star in our example that we were talking about. Okay, now okay, so wi dash is equals, there will be some amount of math in this chapter. You try to capture as much as possible, but since your problems to solve in the exam are going to be very easy, you don't have to understand all these equations in and out, but it is good to know them. Okay, so I'll say L of wi upon wi. So what I'm trying to do is that you find out the slope of your curve, and then based on the slope of your curve you subtract this from your value. So we started from w naught, and you started from w naught and then w naught and then w1 and w2. Eventually you need to reach wi star. So your new value wi dash is going to be your current value, which is wi, minus the slope, the direction, and this term is called your learning rate. Okay, so the value can be 0.01, 0.001 based on how complex is your equation, or how complex is your loss function that needs to be solved. The smaller the value of learning rate, it is going to take more time to converge, but it is going to become more precise. If you make your learning rate as high, it will take less time to converge, but it may just loop around here and there. Okay, so that's the gradient descent. I can get into more details of this, that if this wi or this becomes kind of a if I want to if I want to take this wi minus yi minus y hat square, and then I do a differential equation for d upon d x upon say y minus yi square, then the x square differentiation is 2 of y minus yi into d by dx of y minus yi. Okay, but I'll skip that for now. I don't want to make this over complex, but there is one concept or one reading which is called as your learning rate, change of learning rate. So what happens that as you come close to your optimized value, or as you go further in your optimization, let's suppose you start with t equal to 0 and you are reaching to t equal to n, the value of learning rate should go down. Okay, so if your learning rate is eta here, it should be say some 1 upon x of eta. Okay, so this needs to decay. So how do you reduce this value? There can be two methods of reducing the value of learning rate. One is called as exponential decay. These kinds of things can be asked. Okay, and what is exponential decay? Exponential is decay that this at time t is going to be your initial value e raised to the power of t, and it can have some kind of a constant. Okay, so that's called the exponential decay. There is another method also to do decay, that is called as inverse decay. Okay, and in inverse decay it becomes inverse, so it becomes 1 upon, or you take the initial value and then you do this kind of stuff. Okay, so that implies that over a period of time this value is going to reduce further and further and further, and it's not going to get stuck in local optima, etc., etc. So this is your gradient descent. Okay, so next reading is about back propagation. Let me not get into the equations of back propagation because they are very complex to handle, but this back propagation happens in model estimation for neural network. So neural network will have, say, neurons in your input layer, and then there can be some hidden layers, and then there is an output layer. Okay, so when you pass a batch of values, for a set of values that goes, or for few iterations, you will, when you reach here, you will find some output, and then you will have the labeled output, which may not always, because you will start with random values. Of course, when you start with random values, your output and your actual values will be very far. So now if you look at the neural network, it is nothing but a combination of your logistic regressions. So your value here is a function of all of this stuff, right? So this is a, let's suppose this is output layer, this is hidden layer 2, this is hidden layer 1, and this is your input layer. Okay, now this output layer is a function of your h2, and h2 is a function of your h1, and h1 is your function of your input. So there is a kind of a chain that is happening here. There is a chain that this value is a function of all these values, and each of these values are a function of in what happened in their layer before and layer before. So since this is a kind of a chain rule, and we'll use the gradient descent, whichever we were talking earlier. So if my if in my first set of values I find, let's suppose there is some difference between the expected and the generated or the estimated output, I find the difference of the two, it can be ordinary least squares or whatever you want to do, and then you propagate that backwards in the same proportion using this chain rule, and you update the weights. Okay, and you do it over and over and over and over and over again till the time you find the most optimized values. And when even with more data, the estimations are not getting better, and you would see this kind of a curve where your this is your iterations, okay, and this is your loss function. So your loss function reduces, and then it stabilizes. So somewhere here you can stop. Okay, so this is called the back propagation, especially in neural networks, and this is how you estimate the model variables coefficients in case of a neural network. Now whatever we spoke sounds good, but then it is not as simple as we speak. There are challenges with this approach, and there are some kind of computational issues when we do all of this. So one issue is we saw that there is a chain rule. So from your output to your hidden nth layer to your hidden n-1th layer, the gradients are going to flow backwards. So now what happens when your gradients become small? Okay, and when I'm saying small, generally the gradients are going to be in 0 to 1. Let's suppose your gradient becomes 0.001 and your gradient before that is 0.0001. So when you start multiplying these gradients, you come very close to 0. Okay, and the problem with coming very close to 0 is that there is no incremental change in your weights. So Wi is going to be very close to Wi minus 1. okay, because your gradients are almost diminishing. So this problem is called as the problem of vanishing gradient. And if we take it to the opposite side, if the gradients become large, then there is a problem of exploding gradients. Okay, how do we solve that? It's not part of the syllabus, not worry, but there are on a very high level, how can we solve this is that you use some kind of activation functions which are less likely to fall into these problems. So we only talk about activation function of 1 plus 1 upon e raised to power minus y. So we only talk about this kind of an activation function, but then there are more better function like RAI and leaky RAI, and these are, like, that becomes linear when it is more than 0, and if it is less than 0 it becomes straight line. So if it becomes a straight line, and or it is less likely to get into vanishing gradient problem. So when is you use RAI or leaky RAI or those kinds of activation functions which are less likely to make you fall trap into vanishing gradients. The second is with respect to regularization. We will talk about this, but this is about making this making your model less complex. The second is called your batch normalization. Okay, in case of batch normalization, what happens? Let's suppose you have values like 0.001 and 0.01 and let's suppose 0.003, etc., etc. So you update these values by so your new values are going to be your current values minus the average upon the standard deviation. So when you do this, you will recalibrate these values into something which are more significant rather than very, very close to 0. Another approach to help you solve this, or to not avoid you to get into this, is use some neural networks which are less likely to fall trap into this, and one of them, that is LSTM, long short-term memory. So these are some of the methods which can help you not to get into this issue. Okay, so let's go to next reading. Okay, so now I think now it's only simple stuff that is remaining. Okay, so there is a reading on accuracy versus interpretability. Okay, I don't think I need to write any equations here, and this is very, very simple to understand that, see, the accuracy of models generally becomes better when your models become larger and more complex. For example, all your large language models or any other kind of a neural network are definitely going to give you good accuracy, very good accuracy. But then they becomes very, very hard to interpret. You cannot explain those models to normal people or to business guys that why are you getting this kind of a response from these models, because it's going to be a lot more number of parameters. These LLMs have 1 trillion parameters, right? So no human mind can explain or understand how those 1 trillion parameters come together and solve a problem. So your accuracy and interpretability are inversely proportional to each other most of the times. You can increase your accuracy, but you cannot go beyond a limit. Okay, most of your black box models are more accurate but less interpretable, and your risk teams or your regulators do not like them. Most of your simpler models, like your say linear regression or a decision tree may not be very accurate, but they are very easy to interpret and understand. So that's on the accuracy and interpretability. The next reading is on regularization. We already spoke a little about regularization in the in chapter 1, I suppose, when we were talking about stepwise regression. Okay, so if you remember, we were talking about stepwise regression, where we said that instead of taking all the parameters, so there are two ways to do stepwise regression. One is you take these variables incrementally and see if your output is becoming better. If not, then you leave it there. And the second was you take everything and you start eliminating one by one, and you find out a balance where your accuracy becomes or accuracy is most optimized. Okay, so that's on your more numerical ways to do stepwise regularization. But then there are two more methods of regularization which we have, which are important with respect to the question that you may get, and that is called as ridge regression, regularization, and lasso regularization. Okay, so what we are trying to regularize, we are trying to regularize these loss functions, so that we don't get into overfitting, underfitting, and those kinds of issues, and our accuracy becomes as optimized as possible. So we know that, you know, we have spoken about it n number of times, that your loss function is nothing but you know, the square of your actuals minus your estimated for values of all the data points. Now in case of ridge regression, you try to panelize this by, okay, let me try to put this red here. So this is ridge regression. Okay, so in ridge regression, you try to panelize this with the squares of your coefficients. Okay, so sum. So you add this term and you say that I am going to increase your loss function in the proportion of the values of the coefficients, and then you put some kind of a term here, lambda, which is a coefficient for this. Okay, based on the circumstances, we can take some value of lambda here. But the point I'm trying to make is that you are trying to create a term here so that you are penalizing large beta i's. Okay, so if there is a coefficient which is large, you will probably tend to ignore that. Okay, because as soon as you add it and then you are again squaring it, your loss function is going to increase significantly. So this is going to control the weights, especially for those where your weights are higher. Okay, so it will also help you to reduce variance, etc. But anyway, let's reach there later. So that's on the ridge regression. Now in case of lasso regression, this is too thick. Okay, let me make this green only. Okay, in case of lasso regression, instead of this term, you add the beta naughts in your mod values. Mod values, of course, because we don't want plus and minus to cancel with each other. Let's call this as lambda dash, again sigma 1 to n. So in this case, since your values are more taken in absolute terms, this is going to, of course, this is also going to penalize your beta naughts, but not in the proportion of only penalizing the large values. Okay, it is going to, because when you square terms, it becomes larger and larger. So this means that it is going to reduce those beta knots which are not needed. Okay, so you can think that this is some form of your feature elimination. You are trying to eliminate some of your features which are not needed. So here in this case beta naught will become 0. Here in this case betas will become smaller and smaller. Okay, and if you want to add both of them together, so green and red, both of them with different parameters, if you want to combine lasso and ridge regression, then you can do that, and it's called as elastic net. So you can get some questions like this, that in lasso regression, what is the term that you add? In elastic net, what is it that you add? So in elastic net you will have this entire thing, black plus red plus green. In your ridge it is only going to be black plus red. In your lasso it is going to be black plus green. Okay, so that's the regression thing that I wanted to talk. The next reading is, hope I'm not leaving anything aside, is on the bias, variance, bias and variance trade-off. Okay, so generally when you start doing machine learning, you will talk about, if it is an equation like this term is generally called as bias. Okay, but here right now what we are trying to say is that if your model is complex, if it has too many values, then this values, the bias is going to become smaller and smaller or insignificant, but then your variance is going to be very, very high. Okay, if it is a complex model. If it is a simple model, then your bias is going to be high and your variance is going to be low, because anyway it is only going to use 1 or 2 parameters, etc., etc. Okay, so anyway it is not going to vary too much, but the bias is going to play a very, very important role. So there is a graph that will come almost all the time, where let's suppose this is your error term and this is your complexity of the model. So if your, so this is your bias. Okay, so as the model becomes more and more complex, the bias becomes less and less. Okay, and this is your second equation, which is your variance. So as your model becomes more and more complex, your variance will increase. This kind of a diagram will always come in your exams. What should actually be done? You need to find some kind of an optimization. This is your maybe optimal value, where your bias and variance both balance out each other. Okay, and we spoke about that linear come modeling the noise and parabola. So this is your optimal, this is your high bias, and this is your high variance. So just in case if you forgot this one, so this is what I was talking about. Okay, so that's on the bias variance trade-off. Let me see if there is anything that is left in this chapter, otherwise we'll close this. Okay, there is one more reading probably. Okay, so very, very simple thing. It's called cross validation. Okay, cross validation and grid search and bootstrapping, etc., etc. So what happens, see, if your data is in abundance, then there is no problem. But most of the time your data is not in abundance. Let's suppose you have only 100 items or 100 entities. Now if you have 100 entities and you split this across, say, 70 for test and 70 to train and 30 to test, your data is actually very, very minuscule. So how do you leverage, or how do you use this data so that you can train or you can estimate your model in the most efficient manner? So what we do, there are multiple techniques. One of them is called as k-fold cross validation. Okay, so what we do, let's suppose we are talking about these 100 data items, and then there is k-fold. Let's suppose k equals to 5. So we split this into 5 parts. So now we have 20 here, and there are 5 parts of 20 each. And then we use these 4 parts to train, and then this part to test. But then we use all the permutations, all the combinations of these 5 parts, so that so in this example we did 1 2 3 4 for train, and we did 5 for test. Then we can do 1 3 4 and 5 to train and 2 to test, and then we keep doing this iteratively till we are done with all these combinations of these 4 parts. And then even in spite of having lesser data, we will still be able to estimate our model properly. Okay, so that's what we do in cross validation. The problem with cross validation is that if your data is ordered, it's a time series or something, then you cannot randomly pick up and put it into k folds and eliminate one fold and go ahead. So be careful. You can only do this when your data is unordered, and it can be taken randomly. There is one variant of this which is called as stratified k-fold. Now what happens, let's suppose you take the example of this credit risk, where you have defaulters and non-defaulters. Okay, so there are non-defaulters, which are worthy of credit, and let's suppose defaulters which are 0, which are not worthy of credit. Now let's suppose in those 100 rows that we were talking, say 87 is your non-defaulters, and let's suppose 13 is your defaulters. So you don't have a balanced data set. So how do you manage this in case of a k-fold? So in this particular case, 87 and 13 are weird numbers, but if they are round figures, we make the k-folds of this and this separately, and then we can pick more from here and less from here when we do our training and testing. So we can, based on the circumstances, we can, because otherwise if we make put them together and put some kind of fold, there will be scenarios when you may not have even a single item from here, and you will try to make your model more overfit in terms of non-defaulters. So in case of stratified k-fold, you put them into separate buckets, and then you pick and choose based on your weights, so you can add more weightage here. So let's suppose you say that make this as 60% likely to pick from this bucket rather than 40% from this bucket, or you can change these weights based on the scenario and based on how unbalanced is your data set. Okay, there is a variant of stratified growth which is called as SMOT, which is synthetic minority oversampling. Okay, which is also something similar, but this also says that the minority is oversampled. Okay, So that's the means to live with some of these methods where your data is not so balanced. The other similar thing is called as bootstrapping. In case of bootstrapping, what you do, you generally, so when we are talking about this earlier thing, we were putting into k folds and randomly picking up things. In bootstrapping, you do with replacement. So when I say with replacement, you pick a value and replace it, which means that there is a likelihood that you will find duplicate values in your picked samples, and there is a likelihood that some of the values are not picked up at all. Okay, but what happens is, let's suppose again you have 100 samples, you put them together, and then you pick up 100 values with replacement. So you, let's suppose you picked up 10th value. Okay, you add this back into the superset. Then you pick up another value. You pick up 7th value. You put it back. Of course, there is a possibility that you may end up picking 10th value again. But then you can do this random sampling with replacement many number of times. Let's suppose so if there are 100 and you pick 100, of course there will be repetitions, but let's suppose you pick 80 only, then you can have a lot of variations of these 80 sets in which some values will be repeated, some values will not be repeated. So this also gives you more flexibility or more likelihood to test, and then you keep the remaining 20 for your testing. Okay, so that's on the bootstrapping. The last reading is on grid search. This is also kind of the scaffold and bootstrapping kind of stuff only. So what happens in case of some of these hyperparameters? We were talking about parameters like your lambda in your regularization, or we were talking about some of these learning rate kind of parameters in your gradient descent or neural network, etc. So if let's suppose we are talking about learning rate, we want to see whether we want to take it as 0.01 or we want to take it as 0.01, or maybe we want to take it as 0.1. So now in this case, in grid search, let's suppose we'll make a grid kind of a thing, and then we'll say, okay, your learning rate, let's suppose this is your learning rate, 0.001, 0.01 and 0.1, and then you do these k folds, okay, on your x-axis, and then when you find out these permutations and combinations of these k folds, you get some values here. So you do k fold, you find out various hyperparameter values, and then you run them across those k folds, and then you find what is the most optimized value of these. Where do we find the most optimization? So you find it here, or maybe these are your mean values of this, and if you find this, then you pick up the learning rate as 0.01. The problem here is that it is computationally very expensive. You need to pick and choose so many things that you'll end up investing a lot of or wasting a lot of compute time. So hence there are in the real world there are already guidelines that if you are solving this kind of a problem, your learning rate needs to be so and so in the range mostly. So that takes us to the end of this chapter. There is an appendix in this chapter which talks about genetic algorithms. How do we estimate genetic algorithms? But I will skip that because genetic algorithm in itself is a huge subject. There are books on genetic algorithms in itself, and it is related to the biology or the genetic biology of human beings. And then there are so in case of genetic algorithm, there is a function that is called as a fitness function. Then it is similar to your maximum likelihood thing, but your fitness decides how good your generation is. Okay, it's because it is genetic. There is something called as a mating pool. So when you so there is a generation and you need to find the new generation. You need to find out mating pools, and then you cross them, and then you create new samples. Okay, there are terms called as mutations. So it is similar to regularization, where you try to eliminate some of these values, because over a period of time, if something is not useful, the mutation will make sure that it is eventually eliminated. So that's genetic algorithms. It's in appendix. It's just a casual reading, but this is more to do so with unstructured method to find parameters for parameter estimation. Okay, it's a unstructured method, and there is no need for gradient descent and those kinds of things, and this is genetic algorithms. So that brings us to the end of this chapter. We'll start with the next three chapters. They are simpler and smaller, and this chapter is also very important. Meet you in the next video. Thank you.